All right. So we are ready to continue on. I don't know whether you guys have tried doing the balancing of the redox reactions. I know several people had tests in different classes, and I understand that. I will tell you right now, the quiz, not this Friday, but next Friday, will include you having to balance an oxidation reduction reaction, or two, probably just one. And I will have you do that written out. So that's one of the things that you're going to be aware of, is that that is coming up. The second thing is that I will have a PowerPoint on chapter 19 that I will post to the Canvas site, as well as I will also put up there a video recording of me going through that one. That'll just be a Zoom recording of me going through the PowerPoint and talking through it. So feel free to spend some time doing that. It might be a good addition to reading the textbook on this one. But I think I will cover most everything in the Zoom lectures, both today and next Wednesday, that we need to be aware of. I will tell you right now, the lab that is due for this one, Monday is Easter Monday. We don't have school Easter Monday. I did not make the lab due on Monday. It's going to be due a week from that. That will give us a chance to cover a significantly greater part of chapter 19 before we get to that. So with that, there's one thing in particular that we need to go through today. And we went through balancing oxidation reactions, but we're going to look at a really simple one today. We're going to take zinc solid plus copper, and that's going to give us zinc plus copper solid. Okay, so a very simple one. If we want to go ahead and assign our oxidation numbers, we can do that, but that's going to be fairly simple. I want to write my two half reactions. The first half reaction is this. This is our half reaction. The copper, whoops, helps if I write the reaction. Okay, it's not even Monday and I'm messing up here. I need to write it like I wrote it up here. Okay, so I'm going from zinc to zinc 2+. That's an oxidation. Okay, so I have an oxidation, I'm losing 2 electrons. I have a reduction, I'm losing 2 electrons. Now they're called half reactions because we can actually separate them out into two separate things. I can have a copper solution and a piece of copper, and a zinc solution and a piece of zinc. And if I connect those two by some way of having an electrical connection, a wire external where electrons can move, and a salt bridge or something to where ions can move, I would have a complete circuit. And we can even draw them out. Okay, here, let me make the copper blue because we know copper is blue. So this is going to be our copper solution here. So I've got Cu making it hard for me to read here, and for you probably. So this one contains copper 2+. I have a piece of copper here. The other one over here, I have zinc 2+ and a piece of zinc. Now, separately, they're not going to do anything. They're just going to sit there. The zinc is going to sit in the zinc solution, the copper in the copper solution. But if I connect them by means of some kind of a salt bridge, now that can be a thing packed with salt that is wet. It can be just a piece of filter paper that has a salt solution on it. Anything like that will work for a salt bridge. There are some containers where there is a container here and a container here and a porous disc in between, which is basically unglazed ceramic, and that also allows ions to transfer. Any of those will work, okay? But the salt bridge is necessary because we have to have a complete circuit. We should know some things about electricity. I'll talk about electricity again here in a minute. And if I connect these two here, I will actually have a current flowing between these two. Now, if I were to hook these up, if these were both 1 molar solutions, I would get a reading of 1.10 volts here. Volts is a measure of electrical potential, okay? Now, I have here what is known as a diagram of an electrochemical cell. We're going to go ahead and separate this out a little bit and just look at things a bit different, okay? Now, before I can go back to this, now I'll come back to this here in a minute, but I need to use an analogy, okay? Because we all understand that electricity, if you have the light switch off, the light doesn't go on. If you have the light switch on, it'll go on. Or I can have other things, like my light that I have here. If I pull on this string here, the light goes off. If I pull it back, it goes on. What that does is rotate something that completes a circuit when it's on, or breaks the circuit in order for it to go off. Okay, one thing we know about electricity: no complete circuit, electricity doesn't go. But there's a couple other things, and I'm going to relate it to water, okay? And I am going to make a town, and this is a nice flat town, okay? And if I have this little house here, okay, no door in the house, okay. Here's a house, okay? How does water get to this house? Okay, well, there's a couple things. I could have some kind of a pump or anything. But in small towns especially, a lot of times we have these big things called a water tower. Now, water towers work because there is a potential difference. In this particular case, it's a gravitational potential difference. I have water up here. It goes through pipes, comes through, and goes to here, okay? It's a fairly simple thing. The water flows from here to here because the potential is great. The same thing can happen with electricity. Electrons go from an area of high potential to an area of low potential. It's just going to flow just like that. Now, be aware there's another property here. Now, if I have a really, really small tube here, a really small pipe, a small amount of water is going to flow. If I have a really large pipe, a larger amount of water is going to flow. But the height difference doesn't depend on the amount of water flowing through there. So in electricity, when we talk about the amount of current or amps, we'll cover that next week, flowing through there, that has to do with the size of the pipe or the amount of water that flows through there. For potential difference, we are only looking at height difference, okay? Now, one of the big things that we're going to look at on this is how do we determine that? Now, this one is pretty simple. I have a house here, I have the water here, all I have to do is find the height difference. What if, instead of this nice system here, I have that house and some other houses, and over here, I have another house, okay? Notice this house is not at the same place. Well, in order to find the difference, first thing we need to do, obviously if I can see up at the water tower, it's going to be fine. But if I have some stuff here that's going on, maybe it's a big city and there is this skyscraper here, I can't just tell from that, okay? What I've got to be able to do is compare it to some measurement, okay? So in this case, we're going to use the ground and we're going to define it as 0, okay? And this is going to be above 0, and this is going to be above 0. But this has a greater difference. It's going to have a greater potential difference than this is going to be. Water will flow. Okay? We're going to do something similar with electrochemistry and electrochemical potential. Now, in order to figure out what to define as 0, we all need to compare them to something. Now, with the copper and the zinc, the way I had that written, the electricity is going to flow. We do have a higher potential to a lower potential. We'll look at how we can tell whether some electricity is going to flow here in a minute. But in order to do that, we need to understand something. So what we've done is we've defined something as 0, as the ground. And that particular one is the standard hydrogen electrode. And the standard hydrogen electrode is normally written to gas. Now, at standard conditions, gases are at 1 atmosphere. Okay, so 1 atmosphere for standard conditions. The concentration of ions are 1 molar, and temperature is going to be 298. So it's just going to be standard temperature, just like thermodynamics. Okay, so this is our standard one, and it has been defined as 0. Now, I could write the opposite. This is the reduction. I could write the oxidation. Okay, and these both are the comparison that we have for 0. If I have a reduction, I compare it to the oxidation here. If I have oxidation, I compare it to the reduction here. This gives me our values. Now, along the line, there is this group called the International Union of Pure and Applied Chemistry, and there was this debate to go on to which one to list. And it turns out that the argument won out that we should list everything as far as reduction potentials. So if you look in your book on page 738 or in the back of the book, I think it starts on 834, there are tables of reduction potentials, okay? And if I look at the reduction potentials, it is going to give me a value here, E0. That E represents the electromotive force. Sometimes that's written as a little EMF. Both of these are measurements of the cell potential. These are the same thing. A standard EMF and a standard cell potential would have the little degree sign indicating they're at standard states. And by looking these up, I can determine what the reduction potential is. Now, interestingly enough, if I write the reduction potential or if I write the oxidation potential, the only difference is the sign is going to be switched. So let me look at the reduction potential for copper, okay? So I'm going to have Cu2+. Now, be very much aware, there's also a reduction potential for copper 1. There's also a reduction potential for copper 2 going to copper 1. But this is why the entire half reaction is important. So if I look this up in my standard reduction table, and this is page 738, I'm just going to hold it up here. No, you probably can't read it, but you can see that I'm reading directly from the book. And if I find copper here, I find that my standard reduction potential is 0.337. The reaction that I had before, where I had zinc and copper, I have my reduction potential. Now, my other half reaction is the oxidation. Now, I don't have any oxidation table in my book. If I look for an oxidation table, there isn't one. However, I can find the oxidation. Now, your book goes through all these things about, taking the cell potential of the anode and the cathode and doing a subtraction and everything. I think it's much simpler, write the reduction potential as it is. If I look up this, I will find this reaction. And if I find the E0 for that, in here, it is going to be negative 0.763. Okay. That's the reduction potential. The oxidation potential is just the opposite of that. Okay. So if you write the oxidation potential with a proper value and your reduction potential with its proper value, you come out okay. And how did I get this? I looked up the reduction potential because it's oxidation. I reversed the sign. I need to pay attention here because that negative goes with the electron and not that. Keep your sign straight. It will be a lot easier. Now, I find it easier to do this than trying to remember cathode minus anode or anode minus cathode, whatever. You can read through the book and see how they do it if you really want to. But if I write the oxidation potential as an oxidation, write the correct number, the reduction potential there. The overall cell potential is the sum of these two and 1.100 volts. Fairly simple. After some work, it might be easy. Now, the balancing oxidation reduction reactions may not be simple, and they're probably not easy yet, but after some work, those should be both simple and easy, but not short. These, simple, easy, and short. Okay, well, hopefully that second word, the easy one, will come with this. Okay, the other thing, in chapter 18, we looked at whether or not a reaction is going to occur spontaneously or not. Now, there is a delta G relationship between that and the cell potential. Delta G is equal to negative N nav E0. N is the number of electrons that are transferred between the oxidation and the reduction. In this particular case, N is equal to 2. F is Faraday's constant, and I don't have Faraday's constant memorized, so I'm going to look it up here. And let's see. F is equal to 96,500, and there's a couple different values we have. The one, joules per volt mole, okay, volts are going to cancel, is the one we're going to use. You'll also see coulombs per mole. A coulomb and a joule per mole are going to be there, okay? So when I look at these two, I find that I have N, the number of electrons, F, Faraday's constant, and E, which is the cell potential for the overall reaction. So if I add these two together, I get, and this is where my second whiteboard is going to become important here, E0 for the cell is 1.1 volts. That's the sum of the oxidation and reduction potentials for those particular reactions. Notice something. N, positive number. F, positive number. E, if E is positive, delta G will be negative. If E is negative, delta G will be positive, okay? So in this particular case, E is positive, delta G is negative, it's spontaneous. Now, I had somebody ask a question, is N the number of the total number of electrons? N is the number of electrons that are transferred. In this case, 2 electrons are transferred here, 2 electrons are transferred there. Now, remember when we were going through balancing oxidation reduction reactions and you had to find the least common multiple, you know, when you're balancing your electrons? Because the electrons lost and the electrons gained are the same electrons. They're not 2 electrons here and 2 electrons here. These electrons go here. That's why I like to write the oxidation first. But since reduction potentials, I wrote the reduction first. So looking at this, there are 2 electrons. When I balance this, each of these is going to be 1, 2 electrons are transferred. So N is the number of electrons that we're going to see in, okay? So overall, when we have an electrochemical reaction, all I have to do, write my oxidation and reduction, look up the reduction potential for the reduction, look up the reduction potential for the oxidation, and just write it as an oxidation. Switch the sign of it, and then add them together. This can tell us whether or not a reaction is going to occur spontaneously. So I want to go ahead and take a look at another possible reaction. And I'm going to go back to the table that's in the chapter 738. I know there's a lot more in the back of the book, so but I thought I would start with one that's in the chapter in order for us to do this. And what I want to find out is whether or not this reaction will occur spontaneously and what the overall cell potential is going to be. And in case you're wondering, the volts are going to be important. Your standard AA or AAA batteries all are going to have the same voltage. Okay, those voltage are going to be around 1.5 volts. Okay, so if you have a 3-volt requirement, you put 2 of them together and you get 3 volts. Okay. All right, I'll talk more about batteries at another point. Probably I'll spend most of the time that I talk about batteries in the PowerPoint for the chapter, because while batteries are very interesting, it's just literally looking at the reactions and seeing what's going on. So I don't think there's a lot of chemistry we learn by looking at the batteries, other than the fact that, oh, here is this chemistry, here are these common everyday applications of this chemistry that we're learning here. All right, so I want to look at a reaction, and I am going to pick a couple things that are in the book here. And let's look at okay. Zinc 2 plus aluminum gives you aluminum 3 plus zinc. Now, in this particular case, our equation is not going to be balanced quite as simply as the copper zinc example that I looked at. So we're going to list the zinc reaction and the aluminum okay. Looking at this, wow, 3 electrons, 2 electrons. What is the overall number of electrons that we're going to have there? It is going to be 6. 6 is the least common multiple here. So I'm going to multiply this one by, find a marker that works better than that. I'm going to multiply this one by 2, this one by 3, and I am going to carry these up here, 3, 2, 2, 3. Okay. Now, if I go into the equation, delta GE is equal to negative NFE, and for this reaction would be 6, and for this half reaction is still 2, and for this half reaction is 3, and for the total reaction is 6. Okay, but we're not going to worry about that right now. What we're going to look at is just the reduction and the oxidation potentials. Now, this one is our reduction. Okay, it's going to be identical to the one that I find in the book. And if I look in the book, I'm going to find that that reduction potential is negative 0.763. Okay. And I would be putting these farther to the right here, but if I go too much farther to the right, I'm writing on my door, and that's not going to be very visible. Okay, so this one is negative 0.763 volts. Okay. Looking up the aluminum is an oxidation. But if I find the aluminum reduction in here, the reduction is negative 1.66 volts. So the oxidation is going to be the opposite of that, 1.66 volts. Okay. And if I take my handy dandy calculatorial device, I can do this in my head, but I want to go ahead and punch the buttons on the calculator anyway. I'm going to take negative 0.763 plus 1.66, and that's going to give me a cell potential of 0.897 volts. As that's a positive value, we know that is going to occur spontaneously. The reaction happens. Okay, I do this so it keeps stopping there. All right, very simple. Look for the reaction, find the oxidation and the reduction, write the half reactions, and then you can look them up. Some of the half reactions get a little bit bigger. Now, here's the other thing. I can do it the other way around too. Now, let's look at what happens if I just make two random cells. Okay. And again, looking here, here's my salt bridge, here's my two electrodes, here's my voltmeter between the two. What I want to do is find out what's going to happen if I mix, let's put copper on this side, and let's put okay, so this side is a copper, okay? This side is iron, okay? Now, very specifically, this is an iron 2 to iron, okay? My question is, what reaction is going to occur? If I hook these up, electrons are going to move. Are they going to move this way, or are they going to move this way? So how can we find that out? Well, we're going to start out by looking at the two reductions here. So my two reductions, copper 2 plus. And if I look that one up, I looked that one up earlier. That's 0.337 volts. Looking for the iron one, the iron 2 to iron solid. This one gives me negative 0.44 volts. Okay. Make sure I got that right. Okay. So, looking at these two, I cannot have a reaction where both occur as a reduction. One of these has to be an oxidation. Now remember, for a spontaneous reaction, I want the cell potential for the overall cell to be positive. Okay, so which one of these can I change into an oxidation and get an overall positive cell potential? Well, that's going to be easy. One's positive, one's negative. If I reverse this one, if I write this one as the oxidation, I have a overall positive cell potential. And knowing this, I can identify some things. Now, these pieces of metal have names. They are called electrodes. Now, there's even more to that. So let me rephrase this. Let's remember, this is the reduction, and this is the oxidation. Okay. There is an electrode. Now, the electrons are going to go from the iron to the copper. Okay. So they're going to be, the iron is going to be going from iron to iron 2. So the iron goes this way, the electrons go that way. Okay. And the total voltage here is 0.777 volts. Now, since this one has lots of electrons on it, it's going to be a negative electrode. The oxidation electrode is always going to be called the anode. Remember, A and O, AO. Hey, that's pretty cool, AO. Those are some really good initials, right? Now, you can also remember, the vowels go together. And at the reduction, have the cathode. This is going to be the positive for the cathode. the anode. Now, I like the AO thing, but I actually remember it better by anode is a negative electrode. So we have that, okay? So here we have anox and a red cat. Vowels go together, consonants go together. Yeah, the red cat is one that is commonly used, okay? All right, all this because we just look at which ones. Now, remember, in this particular one, I gave you the two half cells, but I didn't tell you what reaction was going to occur. You had to figure that out. Sometimes you're going to be given a particular reaction and ask if this will occur spontaneously. Generally, if you get a reaction that does not occur spontaneously, the reverse reaction will occur spontaneously. Okay, so if you end up with a negative E0, if you write the reverse of that reaction, that's going to give you a positive E0. And if you hook up those cells, that's what's going to happen. All right. So looking at this, it's a relatively simple system. Why do we have these reduction potentials? Because compared to hydrogen, this is going to have a reduction of 0.337. Compared to hydrogen, this is going to have an oxidation potential of 0.444, or sorry, 0.44 volts. Let's do one more. Okay. One more example. Without drawing everything out, even though drawing everything out is important, you need to be able to do this. It's even more fun if you actually go into the lab and put this together. And if you look back at the time when they were first determining, they first using electricity. Okay. The electricity, they would have actually, a big container with pieces of metal sticking in it. And actually, they eventually came up with alternating plates of zinc and copper and different things that were there. All right. Let's look at one more. And again, page 738 is where I get the reduction potentials, although there are some reduction potentials that are not in that table. This is just a short table of it. I think the table in the back of the book is 2 or 3 or even 4 pages. Okay, so page 738. And I want to look at one more before we go on. And I'm going to stick with things that are on this page, I hope. I was looking to see if it's on here. Yeah. All right. So let's see. I have iodine. What I want to see is if this is going to occur spontaneously. Will iodine change the bromine to liquid bromine and give me the iodide ion? Okay. So how am I going to do this? Well, again, I need to look at reaction and I need to assign oxidation numbers. That's going to be relatively simple. These two are elements in their standard state. Iodine is a solid, bromine is a liquid. I know those, but you can also find them in the periodic tables a lot of places. Bromine is one of the two substances liquid at room temperature. This is going to be a -1 and this is going to be a -1. Remember, monatomic ions have the charge of the ion. Okay. So my two half reactions. Now there's a couple of reasons I'm writing this. Our first half reaction, I2 goes to I minus. Whoops. I need to leave room for electrons. Okay. Now, we have a problem here. There's 2 iodines here, 1 iodine here. I cannot balance electrons if I don't have an even number of iodines. Since iodine changes its oxidation number, I need to have 2 here. Okay? So, 1 iodine goes to 1 iodide, and it takes 1 electron. However, I have 2 iodine atoms going to 2 iodine ions, and it needs 2 electrons. Likewise, bromine going to bromide liquid. Again, 2 bromines here, 1 bromine here. I need 2 of those. So when I do this, I carry my 2s up there. Now here's my question. If I look at the E0 values, am I going to get a total of a positive or negative value for the overall cell potential? Looking up the iodine. This is easy. This is the reduction. I just find the reduction on here. Looking at the reduction potential for this one, I find it about halfway through the page, and that is going to be 0.535. And that's volts. And I'm not going to write volts on there because I didn't leave myself room on the board, but you should write volts there in your notes, okay? The second thing, looking at the bromine plus 2 electrons gives me 2 bromides. Now again, that's going to be the reduction. I'm going to look for that and then take the opposite value of that one. That one happens to be a positive 1.08 volts, or if I write the oxidation potential, that's negative 1.08 volts. So if I do my handy dandy calculator and I take 0.535 plus a negative 1.08, I end up with negative, oops, decimals in the wrong place, negative 0.545 volts. Will this reaction occur spontaneously? No. Now, if I have bromine liquid and iodine ion, I will get bromide ions and iodine solid, but this reaction will not occur in there. So we can use this to do this. So this simply means the reverse reaction is, somebody asks, is the reverse reaction more spontaneous? The answer is the reverse reaction would be spontaneous. However, if you have bromide ions and iodine solid there, and you don't have these, nothing is going to happen when these 2 are mixed together. Okay, so that's one of the things that's going to be really important. Imagine you are trying to put together an industrial system, and in that industrial system, you are using, for example, let's use a stupid example here of people using iron pipes to run things through there. Well, we need to pay attention if there's iron pipes to a particular reaction that's going to happen here. Okay, there's lots of things that would cause iron to go to iron 2. So iron pipes are generally going to be a bad idea for a system because there's a lot of different chemicals that would cause this particular thing to happen. Why is that bad? Well, if your iron pipe is a solid and your iron is reacting and turning into iron 2, it's no longer solid iron and you are going to lose your system. Kind of important. Also, somebody's like, oh, well, here, I have this piece of iron and let's put some other things there. If I put 2 metals together, I can end up with a battery system real easily. So that's one of the things. I will talk probably in the PowerPoint about what it means to be galvanized because that's going to be important. Basically, it's saying, all right, so the iron can easily react here, but let's give it something that's going to react even easier in order to sacrifice that. All right. Okay. I could go through more here. I could go through and start talking about non-standard conditions, but I don't want to do that at this point. It's Holy Week. We have these reactions that we should be able to do. This is actually way simpler than balancing oxidation reduction reactions. But if we can't write our half reactions, we can't do it. The last thing I want to say before we close out here is if I look at this, okay, if I look at my electrochemical cell, have my solutions here. Standard is 1.0 molar. If I have a gas, though, what am I going to do if I have a gas? How do I do hydrogen? Well, if this is hydrogen, the H plus is going to be 1 molar. What's going to happen is we're going to give a platinum electrode here. Okay, platinum is inert. Platinum is not going to react at all. But I'm going to put it into a system here, and here is going to be hydrogen gas in that system with a platinum electrode in it. The electrons will travel through the electrode, and the hydrogen gas is there. The hydrogen gas will be at 1.0 atmospheres. The hydrogen is going to be 1.0 molar. Ah, pH of 1. Okay, so these are our standard conditions. We will look next week at how to do non-standard conditions. In the meantime, for the lab this week, I've sent you to a simulation site, and you can play with making different cells together. So one of the things you might do is look at some of the metals they have and see, predict what do you think is going to happen if I put particular cells together, and see. We'll look at what effect concentration has on electrochemical cells later. In the meantime, I am just going to give a moment if anybody has any questions. If not, let's see. Will future lectures use the same Zoom ID? Yes, although I will still send a link out every time if that's okay. But you can just set that up there. I've tried to set up Zoom as a recurring one for general chemistry, but it just locks up my entire computer. I don't know why it won't just let it go. But it's going to use the same Zoom ID every time.
So we don't have class tomorrow, right? I mean Friday?
Friday or Monday.
Or Monday, okay.
We will not have class Friday or Monday. Our next class will be Wednesday, okay? I will tell you right now, the lab that I will put up next week is going to be one on radioactive decay, and we will cover that radioactive decay using a simulation. That will happen before we even open the chapter on nuclear chemistry. Now, the thing about this is radioactive decay is just first order kinetics. So we'll get a chance to see some first order kinetics in action in a simulation where we'll do some manipulation of the data, but it's also going to give us a good introduction to nuclear chemistry. So we're going to do the lab before we even start the chapter on that. So next class is next week. Next Friday is going to be a quiz, and that quiz is one where I'm going to have you write out stuff, take a picture, send it in. That quiz will be from 10 to 10:50 on next Friday, and I will tell you what days that is next Friday. Okay.
So no quiz this Friday?
No quiz this Friday because it's Good Friday. Holy Week this week. The 17th is the next one we have. So we will have a quiz on the 17th. There will be no Zoom class on the 17th, just a quiz. And that's going to be one where I expect you to write it out. I will give you probably a Word or PDF document of the quiz, but just ask you to write out your answers on a piece of paper, take a picture, and submit it. If anybody has problems with that, please email me separately. Lab and take-home test is both due Monday, April 20th. Yeah, unless you want me to make them do earlier. How many questions on the quiz? About 3 to 4. Okay, I take that back. Okay, one of the questions will be balancing an oxidation reduction reaction. Notice there's a whole lot of steps to that, and you will get points for that. One of them will be just kind of like I did here. I will give you 2 cells and ask you what the overall reaction is and ask you to diagram the cell, and then I will ask you questions about that cell. Okay, those are the 2 parts that are going to be on this quiz. So one is just balancing oxidation reduction reaction. One is just going to be on electrochemical cells, and the information I'm going to ask you to identify the anode, the cathode, and stuff like that. So in reality, there's 2 questions, but that doesn't mean that there won't be more things you have to answer than 2. So I do think this is one that a lot of people could get done in like 10 minutes, but I'm going to give you the full 50 minutes for you to be able to do that. If you're going to have any trouble writing out, taking a picture, and submitting in that amount of time, please contact me ahead of time. All right. So with that, seeing no other questions, I am going to go ahead and quit this. I don't know if I had this setting properly, so forgive me if when I put the recording up, I end up with just a little picture of me up there. Sorry about that. I have been trying to get the settings on this consistent, and I had them correct one time so far. But if nothing else, you'll at least have the audio and a little teeny picture of what was going on for me to be able to do. All right. With that, everyone, have a blessed Holy Week. Have a great and wonderful Easter. Even though you're staying home, celebrate the resurrection of our Lord. With that, have a good week.